Recording. There we go.
As scientists have done experiments and learned more and more about atoms,
We're just going to press pause for a moment because I need a copy of this as well. So actually, no, we're not on page 1. I lied to you. Liar, Miss Spence. No. We are on page 5. Page 5. Let's make this a little bit less. There we go. I can't read that. Okay. So we are going back in time today to the very start of people thinking about atoms. Now, turn the lights down just a little bit. See? A bit better. All right. The sound quality is not awesome, so I'm going to put on the subtitles as well. Okay. Let's see. Subtitles. There we go. Okay. The reason the sound quality is not awesome is because this was made like 15 years ago or so. Okay.
As scientists have done experiments and learned more and more about atoms, they've changed the way they think about atoms. So in this video, we're going to look at a timeline of the different ways that scientists have pictured or imagined atoms over the years. Now, the first people to really talk about the idea of atoms were the ancient Greek philosopher Democritus and his teacher Leucippus. They lived about 2,500 years ago. And Democritus, he said something like this. He said, imagine you have an object, like say a slice of bread, and you cut that in half. And then you take half of that and you cut it in half. And then you take half of that and you get the idea. Eventually, he said, you're going to come to something that you can't cut in half anymore. And he called these objects, he called them atomos, which means uncuttable.
Okay, so let's take a moment and fill in our sheet here. Early ideas about atoms. Approximately how many years ago? 2,500. So you can fill in that first box, 2,500 years ago. Democritus and Leucippus, 5th and 4th centuries BCE, came up with the idea that there was some particle or other that was uncuttable. So you can fill in uncuttable in that box on page 5.
And it's where we get the word atom from. Democritus imagined that all matter, all stuff, was made of these tiny, uncuttable particles. And he imagined that the atoms came in different sizes and different shapes. He imagined, for example, that iron atoms had hooks, which is how they could hold together so strongly. And he thought that salt atoms had spikes on them because he felt that salt tasted sharp. So, Democritus was right. But people didn't really take to his ideas. Part of the reason was because around the same time, the well-known philosopher Aristotle proposed his own idea of what matter was made of. He said that different things were made of different amounts of the elements earth, water, air, fire, and ether. This is kind of like Captain Planet if you're old enough to get that reference. And more people,
even I'm not old enough to get that reference,
believed Aristotle, maybe just because he was so popular already. So Democritus and Leucippus, they were right all along.
And then they got forgotten about. Poor guys.
But here's the thing. They weren't scientists. They couldn't do experiments in the laboratory to prove that they were right. And because of this, some people think that their idea, it was just kind of a lucky guess.
So these guys were good guessers, not good scientists. Okay? Good guessers.
They couldn't actually prove what they thought. So, how can you tell whether it's right or wrong? Ideas about atoms remained that way for about 2,000 years. Until in 1808, the British chemist John Dalton came up with the first scientific experiments that showed that matter was made of tiny little particles. This is kind of how John Dalton pictured atoms.
Okay, so we're going to just pause here for a second so you can fill in. On the workbook, we have Dalton's model of the atom. So take your pencil, fill that in, Dalton's model of the atom. And he said that matter consists of indivisible, not invisible, indivisible What does indivisible mean? Yeah. You cannot divide it up. Does that sound a little bit like uncuttable? So here we got a guy who's kind of given us the same idea as these Greeks, you know, a couple thousand years earlier. All right. And the atoms arrange in different combinations, so fill in combinations, to make different compounds. They arrange in different combinations to make different compounds. And at the bottom of the page, you can fill in John Dalton. And I don't think Tyler gets around to this. So there's a box at the bottom. It says this model is called the billiard ball model. Do you guys know what a billiard ball is? Have you ever seen the game Pool? You know, where people, you know, like this kind of thing? Okay, those balls are called billiard balls. And that is how Dalton imagined the atom, is that, can you imagine dividing a billiard ball? It would be very difficult, yes? And when they hit each other, they bounce off each other very nicely, yeah? So that's what he thought they were like.
Imagine them sort of as tiny little balls that arranged in different combinations to make different things. And he imagined that these atoms were indivisible. You couldn't cut them into smaller pieces. Now, at first, nobody believed Dalton. But over the course of the 1800s, more and more scientists did begin to believe what he had to say. But then in the 1900s, the early 1900s, people's idea about atoms started to change. One of the key things that caused this change was that in the late 1800s, J.J. Thomson discovered that atoms have electrons. And he discovered that electrons are much, much smaller than atoms.
So what we're going to do is we're going to flip to page 6, if you have not already done so. And we are going to fill this in. What is the name of J.J. Thomson's model? It is the plum pudding model. Ooh, plum pudding. Plum pudding. And you'll notice that there's that little circle with a line in it. And what is that? That's an electron, okay? So you can fill in the little box with the little circle with the line. That is an electron. And then the little positive box, that is the positively charged pudding. So that is our positively charged pudding.
So while Dalton thought that atoms were tiny and indivisible, J.J. Thomson said, no, they're not indivisible because they're made up of electrons, which are much smaller. So J.J. Thomson pictured the atom as sort of like a blueberry muffin. He called this the plum pudding model. J.J. Thomson imagined...
Now, the reason that Tyler is referring to it as a blueberry muffin is we are probably all familiar with what a blueberry muffin is. Yes? Are we all familiar with what a plum pudding is? No. Okay, so you can imagine a blueberry muffin instead of a plum pudding.
Imagine that if you took an atom and split it open, you'd see tiny electrons stuck throughout the inside of it, just the way blueberries are stuck in the dough of a blueberry muffin. And Thomson thought that what's the dough in a blueberry muffin? That it was like a positively charged substance. So you had negative electrons stuck in like a positively charged dough. And together, the positive and negative charge balanced, the two things balanced each other out so that the atom was electrically neutral.
All right, and this is on that little paragraph there. So if you read along with me, it says the positive and negative balanced each other out so that the whole thing was electrically, anyone catch that word? Neutral.
But the big change from Dalton's model to Thomson's model was showing that atoms weren't actually indivisible, that they were made of even smaller things. Now, not too much longer, in the gold foil experiment, Ernest Rutherford discovered that atoms had a nucleus, that all the positive charge in an atom was concentrated right in its center, and that besides that and the electrons, atoms were pretty much empty space. So J.J. Thomson thought the positive charge was all distributed throughout, like dough in a muffin, but Rutherford showed that all this positive stuff was concentrated right here in the center.
Okay, so let's go through and fill in a few things here. What model is this called? The nuclear. How do we spell that? And then it just looks like the word clear. Nuclear. Nuclear. Okay, nuclear.
And this is what we call the nuclear model of the atom because it has a nucleus. Sometimes.
So you can label that thing in the middle, although he has his hand over it right now. Let's go back. That is the nucleus. Have you guys ever heard of a nucleus before? When did you hear about a nucleus? Last year. Where was there a nucleus? Yeah. Yeah, in the body. In what part of the body? In a cell. And where in the cell would you find the nucleus? So if you have a single cell, where would the nucleus be? In the middle. So guess where the nucleus is in the atom? Also in the middle. Okay, so that is our nucleus. So you can fill in the little box that says nucleus. Okay. And in the little paragraph there, actually, we could do this together. Let's just grab this here. There we go. All of the positive charge, according to, oh, and what was that guy's name? Ernest Rutherford. Okay, Ernest Rutherford, and that is the nuclear model of the atom. And there is the nucleus. Rutherford said all the positive charge in an atom was concentrated at its center. Besides that nucleus at the center, atoms were pretty much, anyone remember? Empty space, yeah. Okay. And we're going to carry on with our little video. There we go.
In the center. And this is what we call the nuclear model of the atom because it has a nucleus. Sometimes people call this the Rutherford model. Now, so far we've been talking a lot about the positive charge and the nucleus of an atom. But we haven't talked too much about what's actually going on with these electrons in the atom. And in 1913, the physicist Niels Bohr came up with his model of the atom. He reasoned that there was a nucleus in the middle, just like Rutherford had, but that electrons, instead of just sort of being randomly distributed throughout the atom, Bohr said that the electrons were sort of like planets around a sun, that they were spinning around the nucleus in circular orbits.
Okay, so we're going to fill that in together once again. So this one is a weird spelling, and everyone always gets where the H goes incorrect. It's first a B and then an O. Okay, so it goes B-O and then the H and then the R. If you misspell it, it is not a big deal, but that is how it is correctly spelled. Okay, so and this guy doesn't have a different name for his model. It's just his name, Niels Bohr. Was he Danish? I feel like he might have been Danish. Anywho, there was an old name for these places. He thought that these electrons went around like planets around the sun. And so because he thought they were like planets going around the sun, he called them orbits. But we're not going to use the word orbits because it is outdated. We're going to use the new word where we call them either shells, or we can call them energy levels. While we're here, we might as well label what this thing is. What's that thing? That's an electron. What's that thing in the middle? That's the nucleus. So in this one, we have shells or energy levels. We got the nucleus. We've got the electrons on the shells. And so the electrons go around the nucleus in, I'm going to say shells because that is the more up-to-date correct term, at specific distances from the nucleus. Oh, I guess I could have called it orbits because now we have a place. The new name for orbits are shells or energy levels. I guess I should have put orbits in that first blank, but that's okay. It's okay if you wrote shells there, it's fine. The really cool thing about the atom is that some of the experiments that they did to see how they came up with these ideas are simple enough that we can actually visualize them ourselves. And we're going to do a little bit of that. Okay? But before we do that, we're going to finish all the models of the atom from back when till just right now. Okay? So off we go back to Tyler.
So here are a picture of some of the electrons, and here are the orbits. Imagine that they're spinning around the nucleus in these circles. All right. Now, people thought Bohr's idea for the electrons made a lot of sense at first, but then in the 1920s, additional experiments showed that it wasn't exactly the way electrons really move. And a variety of physicists, particularly the physicist Erwin Schrödinger, showed that electrons weren't really spinning in orbits, but it's more like they were hyperactive flies, and they were buzzing around the atom, sketching out different shapes. It's kind of if you did like time-lapse photography on a hyperactive fly.
Okay, because everyone's trying to fill it in. We'll fill it in together, and then we'll come back to Tyler. Okay, so we've got here, this is called the quantum, Q-U-A-N-T-U-M, quantum mechanical model of the atom. And here's the crazy thing, this guy's name, normally if you have the sound sh, that's S-H, right? But this guy, it's S-C-H. Stro. Stro. And then the last part of the name is easy. Hi. What's up?
I won't disturb you right now, but I just wanted to ask something.
Okay.
But I can wait.
Why don't you come in and ask me now? They could probably use a break, right? Yeah, just chill for a minute. Otherwise, you could be here a while. Yes. And you did not get it yet. There you go. You bring it back to food. Okay. And if you have any questions, you can ask. Yeah. Okay. All right. The last part of this guy's name is Dinger. Dinger. Schro. Dinger. Schro. Dinger. Now, how excited am I going to get if you cannot spell this properly? Not too excited as long as you get pretty close. I'm a happy camper. Yes? Okay. Now, this crazy little wiggly woggly line, that wiggly woggly line is called an orbital. Not an orbit, but an orbital. And this is not just called the quantum mechanical model, that is one name for it, but it has a different name as well. You can imagine that this little area here is a bit like a cloud, yes? And do you remember he was talking about these crazy hyperactive flies that buzz around and draw out these shapes like a cloud? Those little hyperactive flies, those are electrons. So that's why we call it an electron cloud model. So if you don't have anything to highlight with, you can just underline it. This is also called the electron cloud model. And so the electrons don't spin around in orbits. It's more like they are hyperactive flies. And they buzz around, sketching out these different shapes. So one of those shapes looks like a sphere or a ball, okay? If you have another one of those shapes, what did we call those weird shapes? Orbitals. Another orbital is shaped almost like two teardrops. Or two balloons. So I need to be having that. Yes, okay, let me pick that for you, and I know probably where I'm from. Yes, okay. Cool. I will fix that for you. Okay, cool, thank you. So if you take time-lapse photography of these hyperactive flies, you will get a particular design. You might get a sphere, you might get 2 teardrops, you get even crazier and crazier over time. These hyperactive sketch-out shapes are called orbitals. Some of these shapes were spheres and other look like 2 teardrops next to each other. Oops, sorry. We good? Okay.
And you saw that over a long period of time, it sketched out a particular design. And whereas Bohr called these circular paths, he called them orbits, Schrödinger called the hyperactive sketch-out shapes, he called them orbitals. Here's a circular orbital too. But electrons didn't only make circles. This is actually a sphere because it's a circle in 3 dimensions. Here is another shape, another type of orbital that electrons could also make. Looks like this, sort of 2 teardrops next to each other. So in the quantum mechanical model, electrons don't orbit the nucleus. They buzz around the atom, sketching out different shapes. Now let's focus on the nucleus here. Over the same amount of time, and a little bit later, scientists were discovering the 2 subatomic particles that make up the nucleus.
Does anybody know the 2 subatomic particles that make up the nucleus? Oh, I'll take one from here and then I'll take one from over here. Yes. They had protons and the other one, neutrons. Sorry, Spencer. Okay. If there had been a 3rd particle, it would have been yours. It would have been yours. Yeah. But we already had electrons, so there we go. Ooh, anyone know what all of these things are made up of? Anyone remember it from last year, what all these subatomic particles are made of? Quarks, yeah. We won't talk about quarks at all. You'll probably never see a quark again until university. Because really, they don't have a lot to do with the chemistry of how chemicals react with one another. So they're not useful until you hit some fairly high level physics. Okay, so that's why we don't see them again for a while. All right.
So we can refine this picture a little bit more. In 1919, Ernest Rutherford discovered protons. There they are. And then in 1932, James Chadwick discovered neutrons. So the really correct view of the quantum mechanical model shows the orbitals being sketched out by the electrons, but then also shows the subatomic particles, protons and neutrons here in the nucleus. Now, this is pretty much how we think about atoms today.
All right, and let's fill that all in together. Here we go. All right, what was that model name again? Quantum mechanical. Now, is there another name for the quantum mechanical model? Also known as the electron cloud model. But this one now includes protons and neutrons. And the protons were discovered by Ernest. Do you guys remember Ernest's last name? Rutherford, yes. And then the neutrons were discovered by poor old James Chadwick, who usually just gets mentioned in that James Chadwick discovered the neutron. If you're interested in how that came to be, how he discovered them, you can watch Tyler DeWitt's video on the discovery of the neutron, but that's going to be like something you could do on your own time, okay? Wonderful. Okay, what are the black ones? Not that they have to be the black ones, but what are the black ones? Those are the protons. What charge are protons? Positive. And the white ones are neutrons. What charge are neutrons? They are neutral. So we could put like a little circle with a 0 in it, okay? And then in this orbital, we have electrons. And this whole thing in here is the, what's that whole thing in there? Nucleus. So I got a question for you. And my question is this: what charge is the nucleus? It's positive because it's got positive things and it's got neutral things. And if you have positive and nothing, then you have positive. What charge is the area outside the nucleus? Oh, thank you very much. Wonderful. What charge is the area outside the nucleus? Pardon me? Negative, yep. Negative. Because it's got electrons in it, yeah? Mostly it's empty space, but whatever, if you ever run across a charge in there, it definitely is negative, okay? So the nucleus is positive and everything outside of the nucleus is negative. And the protons and the neutrons are located in the nucleus, yes, of the atom. Okay.
But as scientists learn more and more about atoms, as they do more experiments, they're going to find that this model isn't exactly a perfect representation of what atoms are really like, and they're quite likely to change this and refine it even more. Now, as I said, this quantum mechanical model is like the really accurate way to describe atoms. But the thing is, with these orbitals, it can really be kind of a pain sometimes to describe simple things that atoms are doing using electron orbitals. And so a lot of times in these videos, when I talk about atoms, I'm actually going to be sort of using a cross between the very correct quantum mechanical model and the sort of outdated Bohr model. Just because for our purposes, a lot of the simple things we're going to be talking about, the Bohr model, it works just fine. So already you've probably seen me draw atoms like this, where you see the electron orbits at different angles. And sometimes, particularly when we're talking about bonding, we're going to be drawing atoms like this, with the protons and neutrons here in the nucleus, and then electrons in different rings, different orbits on the outside of the atom. We're going to find that thinking about the atom like this is very useful for simple tasks.
Now, how many of you learned the Bohr model last year at all? A lot of you. That's fantastic. Okay, so it will be a little bit of review and a little bit of new this year, okay, on that. All right, and we're just going to let Tyler be for the moment, and we're going to answer a couple of questions here, and then I'm going to give you a little bit of study time. Yes? You sure can. Yeah, just sign out and take the hall pass. Okay, so why would we use the less accurate Bohr model? This is on our next page now. This is now on page 8. So if you're not on page 8 yet, flip to page 8. Why would we use the less accurate Bohr model when it is not as accurate as the quantum mechanical model? The Bohr model is really useful for showing bonding. And it's really useful for showing patterns in the periodic table. So for example, in group 1 of the periodic table, do you remember groups in the periodic table? Okay, groups are the columns. So the very first column of the periodic table, group 1, every atom has 1 electron on its outermost shell. You don't have to draw that, but like it will show you, the Bohr model will show you patterns like that. And every group 2 atom, guess how many electrons are on their outermost shell? 2. Wow, right? So you got, your first shell, you got 1, 2, this one, you got 2 shells, and you got 1, 2, this one, you got 1, 2, 3, and you got 1, 2. Like I said, you don't have to draw this, but this is what the kind of patterns we're talking about, okay, in the periodic table. And then bonding, let's just take a look at water, okay? What is the formula for water? Do you guys know? Water is H2O, yeah, okay? Here's a hydrogen, and it's got 1 electron on its outer shell. Here's oxygen, and it's got 1, 2, 3, 4, 5, 6 electrons on its outer shell. I'm not bothering to draw the inner ones because it's too complicated. Okay, and like I said, you don't need to draw these right now. You can just like kind of look along. Here's another hydrogen with 1 electron. Well, it turns out that atoms are really stable and really happy when they have a full outer shell. And most of the time, full is 8. How many does oxygen have right now in its outer shell? 1, 2, 3, 4, 5, 6. Wouldn't it be nice if we could put those together and hydrogen could help oxygen out? So here's oxygen, and it's got its inner shells. There's its outer shell. And now hydrogen says, I will help you out, oxygen, and I'm going to share one of my electrons with you. And the other hydrogen says, I will also share one of my electrons with you. Now, can you imagine trying to draw any of these things with this? Right? Like I said, you don't need to know any of these things yet, any of those drawings yet, but what you do need to know is that, wow, this is a way easier way of representing the atoms than this crazy stuff with the spheres and the teardrops. And if you have more than one sphere, you've got a sphere on top of a sphere on top of a sphere. How on earth do you even draw that? Right? That's crazy, right? So, and then you've got teardrops on top of teardrops on top of spheres, and it's all in 3 dimensions, and it's nuts. So that's why we do the Bohr model. And we're going to leave it there for today because we have 25 minutes left. And I would like to give you some time to work on the review. And if you have finished the review, you can make some study notes or you can quiz your neighbors. Okay? So 3 things you can work on right now. Number 1, the review. And if you don't have a copy of the review, let me know if you were away or if you've lost yours or whatever. Number 2, you can make yourself some study notes. If there was anything you got wrong on the review that you think, oh, maybe I should write that down, make some study notes for myself. And number 3, you can quiz each other. You could also make flashcards if you wanted to. Pardon me? Yeah. Just make sure you sign out and take the hall pass. Yes. That's a good idea. Perfect. Is anyone lacking a review? Yes. So sorry. I've got the attention span of a gnat. Like, gone. All right, quiz.
How many questions do we have for the test?
For the test, I would have to look that up. Okay. I've just got to grab a copy before I forget, because my brain holds on to things for like. Wonderful. Thank you.
Yeah.
Stop taking my pencil. I only have two. Oh, it's supposed to be very good for your posture. Actually, that is really comfortable. I like it a lot. What? Yeah. Is there anyone else who needs a copy of the review? Yes.